A very warm hello, my name is Johannes Lindorfer. I'm working for the Energy Institute at the Johannes Keppler University in Linz, Austria. The title of my talk is The Pathway to a Carbon Cycle Economy and dealing with green CO2 potential for its valorization. CO2 is unquestionably the biggest threat to global climate, but the carbon and oxygen containing gas has also its industrial applications that are already established, especially in the field of direct use, not just bringing the bubbles to the drinks, but also as solvent in enhanced oil recovery or as heat carrier and others. In the last years, significant development efforts on new fuels, chemicals, and materials from CO2 were made, and the top startups in the field received funding of more than $100 million. Some of these efforts can already be quantified. The growth rates show an upward trend with a current volume of approximately 250 million tons CO2 in use per year. But in relation to the level of emissions, there is clearly still almost a factor 1,000 in between, talking about mega and gigatons, not accounted for in the greenhouse gas balances because most of the valorized CO2 is from biogenic sources. The valorization of carbon dioxide via so-called CCU approaches is a challenging job and highly energy intense, as practically oxidation needs to be inverted. Also catalyzed conversion fight against the second principle of thermodynamics, and the effort increases with the order of the products and bound carbon and hydrogen. When we assess the electrochemical production of methane and methanol, efficient hydrogen provision is a key enabler for maximized efficiency. There is much room to improve CCU efficiencies, but we expect to reach comparable efficiencies for the power-to-ethylene process chain. CCU products are not carbon neutral by default. Total system analysis to evaluate its potential performance in future energy systems is essential. As the project aims for sustainable, environmentally friendly products, the focus is on existing high-purity CO2 sources, such as biogas upgrading and bioethanol production, and renewable electricity from wind and solar power as main resources. Elaborating on the CO2 sources, reflecting the ratio of CO2 in the off-gas combustion process results in a comparable low concentration of 3 to 8%. Air provides concentrations a factor 100 lower. In contrast, biogas from anaerobic digestion contains approximately 60% methane and 40% CO2. If the gas is upgraded to natural gas quality, the off-gas is basically 100% CO2. The thousands of biogas plants in Europe are regionally distributed, and the gas is usually combusted in combined heat and power facilities. But there are also numerous biogas upgrading plants already in operation. So significant potential of 3 million tons of highly concentrated biogenic CO2 for valorization is available in approximately 500 biogas upgrading plants to biomethane in Europe. For biogenic CO2 from bioethanol fermentation, CCU is already technically feasible without extensive effort. Around 1/3 of the CO2 is already captured and distributed, for example, for dry ice or carbonic acid applications for beverages. With the remaining 2/3, accounting for 3.7 million tons, technically are still available as a carbon feedstock. In total, approximately 500 million tons of biogenic CO2 are produced annually in Europe, of which are 86% imply cost-intensive flue gas purification. Significantly related to the concentration and purity of the CO2 feedstock is also the effort and consequently the cost for extracting the pure CO2 stream, as the conversion technologies under focus are highly sensitive towards impurities. Calculating the efforts, CO2 from biogenic sources can provide the lowest capture costs, so below 50 euros per ton. Direct air capture is currently rather costly, with cost of close to 300 euros per ton, due to the fact that just 400 ppm of CO2 is in the air, but we expect that these costs will rapidly be reduced by technological development. With that data at hand, a geographical matching of biogenic CO2 and renewable energy sources was conducted to provide 100% renewable-based products, to avoid the transport of hazardous reactants, and to support grid operation by balancing out fluctuating, locally generated renewable energy. In this map, you see a visualization of identified biomethane and bioethanol plants for CO₂EXIDE rollout scenarios. The same was also done for wind parks and large-scale photovoltaics production. Out of this pool, 3 case studies in 3 countries were picked for detailed production cost estimates, considering local conditions and existing infrastructures. The developed case studies for potential technology rollout consider typical localized electricity production profile. The top diagram is representing photovoltaic, the diagram in the bottom wind. The green base load is reserved for feeding to the grid. The peaks are modeled to be available for power-to-X valorization to avoid usage competition and system inefficiencies, and to provide low electricity input costs for the CCU product. We are currently compiling the data for the case studies to work out a nice publication. As a short summary, I would like to conclude that the scientific and technological challenges in the reductive activation for CO2 conversion to fuels and chemicals is a very dynamic field. Achieving a net zero emission EU energy system by 2050 based on predominantly renewables is a prerequisite for all CCU approaches. A sufficient high price on CO2 emissions of, let's say, at least 50 euro per ton is crucial that CCU is turning economic. For sure, also supportive would be international binding climate agreements. We see the need to identify the range of future-proof CCU technologies and products now, because due to the expected long-term periods to market. So all in all, CCU is a really promising option for CO2 emission reduction, but not an alternative. Thank you very much. With a short snapshot on our European projects in the area of technology assessment, I would like to close my presentation. Thank you very much for listening. And here are my contact details. If you have any further questions, please come back to me. Thanks a lot.